We already have a technology that produces clean, abundant electricity using elements that are available on every continent of the earth inexpensively, so they're accessible to everyone, not just to a few. A lot of times it's mined by children in labor under conditions that the United Nations, UNESCO, they know about it, they've documented. In 2014, they said about 40,000 children were working in mines across Southern Democratic Republic of Congo. Many of them are mining this cobalt. We know that we are surrounded by energy, and we're learning through new physics to tap into that energy. The quantum vacuum. Hello, and welcome to this very special episode of Science, Policy, and Politics. My name is Gregg Braden. I am your host for this entire episode. I have to tell you, I'm especially excited about this episode because it gives me the opportunity to share something with you that very few people in the mainstream are talking about. Even very few scientists at the conferences that I go to are even aware of the technology that I'm going to share with you. So let me begin. Let me just ask you a question. We all know that climate change is a problem. We didn't cause the climate change, but we're certainly contributing to it through the greenhouse gases, particularly the carbon dioxide, that industry, based upon fossil fuels, is pumping into our atmosphere and has been for the better part of a century. So what would you say if I said to you that we have a technology, we already have a technology that produces clean, abundant electricity using elements that are available on every continent of the earth inexpensively, so they're accessible to everyone, not just to a few, that cannot be made into weapons the way that uranium can be converted to plutonium, the byproduct, and the plutonium can be weaponized into the nuclear arsenal that we see between the superpowers right now. That can't happen with this technology. That cannot melt down like a Fukushima reactor or a Chernobyl reactor. It's impossible for this technology to melt down because it works on a very, very different principle. The waste from the technology can be recycled into the fuel in the next cycle, and that we have had this technology for over 60 years. Now think about what I'm saying. Zero greenhouse gases, can't be weaponized, can't melt down. The waste becomes the energy for the new fuel cycle. It is inexpensive, it is abundant, found throughout the Earth's crust. You probably say what I say when I discovered this: where is it? Why don't we have this now? And that is a question that we need to ask, and it needs to be answered if we are in the crisis that we're being told that we are, and if it is so vital that we stop producing carbon dioxide, kicking it into the atmosphere. Why aren't we looking at this technology? Well, that's what we're going to do in this episode. I want to talk to you first. It's a two-part episode, actually. I'm going to talk to you about what we're being told are clean, green, renewable forms of energy. And what we'll discover together is that in a cycle of renewable energy, there are three phases to the cycle, and the only phase that is truly green is when the technology is being used. The application, the implementation. When that solar panel is on your roof, that's the only time it's really green. The production of that solar panel is tremendously energy intensive. It's using materials that are not sustainable from sources that are not sustainable, and it's being mined in ways that are very sad in some respects. The 20-25 year life cycle of a solar panel, where do they go? Where do they go when at the end of their life cycle? Well, that's something that hasn't been thought through very well. And what is now happening is that landfills are being populated with inoperable solar panels that are breaking, toxic materials leaking into the soil. The materials used to make the windmills, to make the motors, to make the batteries and the new electric vehicles, all of that, they're only green in the implementation, not the production, not the recycling. And that changes the conversation. It wouldn't do me any good to say those things to you if I didn't have a remedy. And I'm not saying it is the answer. I'm saying that we're in a learning curve and that there are stepping stones in that learning curve. And we have at our fingertips right now a stepping stone that can address the greatest concerns in a heartbeat if we have the leadership, if we have the will to move in this direction. So I hope you're intrigued. Let's get into it. Let me share with you what the green energy cycle is all about, where it fails, and what we already have to replace that energy cycle. So when it comes to solving any big problems in the world or our lives, individually, collectively, society, scientific problems, we have to ask ourselves a question. And this fundamental question I've always asked when I was in academia, when I was in the corporate world as a scientist. And the question is simply this: how can we solve the problem if we're not honest with ourselves about the problem? Now that might seem obvious, but think about this. How many times do we try to cover up or lessen the impact of what we're facing, and in doing that make it difficult to find a solution because the solution is not really talking about the issue any longer? Well, this principle is especially true when it comes to climate change and what we're being asked to do in response to climate change. You and I are being asked to change the way we think, as I said, the way we live our lives, policy decisions. Entire industries are being asked to shift based on what we've been told. And what we've been told is this: that renewable energy, clean, green, renewable energy is the answer to sustainable electricity. The problem with this is that it is not and cannot be the answer the way that it is being portrayed today. We're told that a world, this utopian world of windmills and solar panels, supplemented with geothermal and hydro and some other things that are out there, are going to revolutionize the world. They're going to give us safe, reliable, clean, green, sustainable energy. The problem is that we're now talking about a world that is going to be needing even more electricity than we have right now. And the question that very few people are asking is, where does that electricity come from? Where does the electricity that we have right now come from? Where will the additional electricity come from? So the ideas themselves, they're good ideas, but we have to be realistic. I'm an optimist. I'm also a realist. We have to be realistic about where we are and what is possible. And I'm going to tell you right now, solar and wind energy are not and cannot be the answer to reliable base load energy that we see across the planet. But there is a solution, and I'm going to share it with you in this presentation. But to get to that, I want to make sense of what it is we're being told right now. So the current energy equation, where does electricity come from right now? 80% comes from fossil fuels, 11% from renewables. Those fossil fuels are made up of natural gas, petroleum, coal. There is some nuclear power in there, about 8%. But look at the 11% of the renewables. Look at what constitutes those renewables. 20% of it is wood. We don't want to cut down the forests of the earth to create the energy that we need, and we don't want to put the burning of that wood into the atmosphere. It's not the cleanest way to go. 20% is biofuels. Where that works, that's great. 24% is wind, 22% hydro. I want to talk to you about hydro. We know climate change is happening. Climate change is the big picture. It's global. Weather patterns are local. Climate change is driving a shift in weather. And one of the places that we're seeing that is in the high elevations. We are not seeing the snowpack that we've seen in the past in the Alps in Europe, certainly, in the Andes of southern Peru, in the Rocky Mountains of the United States, the Cascade Range of the United States. Less snow melt, less water going into the resources that we've relied upon for hydro. We don't know how long hydro is going to be reliable. Only 9% of this 11% is solar and 2% geothermal. So I wanted to give you a sense of what we're talking about, because what we're looking for is a way to convert that 80% from fossil fuels into something that truly is sustainable, reliable, a form of base load energy that will work under any conditions Rain, no rain. Snow, no snow. Wind, no wind. Water, no water. Heat, no heat. Cold, no cold. It doesn't make any difference to the kind of baseload energy that we're going to be talking about. So the question, is solar and wind the answer as we're being told, or is it part of a solution? Is it part of a bridge to what we need in our lives? Now, it's a very unpopular conversation to have. A lot of people don't like to talk about this. How can we be honest or solve the problems if we're not honest with ourselves? I'm going to be honest with you about renewable green energy sources. I love them where they work. I love them when they apply. The problem is that many of these sources, they rely upon environmental conditions, as I just mentioned, that are beyond our control. We can't control the wind. We can't control the sun, how much snowpack we're going to see in the high elevations. They also rely upon raw materials that are not abundant in the earth. Rare earth minerals is what these are called. I'm going to talk about them in just a moment. They rely upon these rare earth minerals. We don't have a 100-year supply of these, and where they are located politically, there can be problems, and the way they're extracted from the earth is presenting a very sad situation for children, for people in countries that are poverty-stricken, and I'll talk about that in just a moment as well. The energy to make the clean, green, sustainable forms of energy, the energy required to make the turbines of a windmill, the energy required to make the windings on the motors that go into the electric cars, the energy required to produce the silica for a solar panel or to produce the frames or the mounts from the solar panel, it takes a tremendous amount of energy. And right now, that is a fossil fuel-based energy. So we're using tremendous amounts of fossil fuel to create what we're being led to believe are green, clean, sustainable forms of energy that in truth are only sustainable while they're functioning. They're not clean, green, sustainable when they're being produced, and at the other end of their life cycle, when they're no longer usable, when they expire, when they stop working, they are toxic in the environment. All right, so they're only green for one part of the cycle. If this is a new concept, I just want to develop this a little bit for you. 3 stages to a renewable form of energy. The application, and this is, I'm just emphasizing this, when it is actually functioning, it definitely is green, and I love that. The solar panel just sits there and generates that electricity. The windmill turns and generates that electricity. That's awesome. However, to get to that point, the production, as I just mentioned, and what a lot of people don't think about, solar panels, for example, have about a 20-25 year lifespan. We are now coming to the end of that first 20 to 25 year lifespan from when solar panels were first introduced. Where are those solar panels going when they can no longer produce electricity? Well, I'll tell you where they're going, and then we'll talk about it. They're going into landfills. In the landfills, the glass is breaking, the toxic elements are leaching into, they're seeping into the groundwater, into agricultural sources. It's a big problem, and it's a big problem all over the world. I'll give you some statistics here in just a moment. So, the production, what does it take to go into these? Solar panels, batteries, those awesome batteries that are going into the electric cars, the windmills, the turbines, they all require these rare earth minerals that I'm talking about. So let's define what it is that I'm talking about here. What you're seeing is the periodic table of elements with the 17 rare earth minerals highlighted. Some of these you're familiar with, some you probably never heard of. You've probably heard of selenium, tellurium, gallium, germanium, cadmium. You may not have heard of indium or neodymium, okay, and I want to get that right, and I apologize for that. You may never have heard of these and others. Where do they come from? Well, this is where it gets a little controversial, a little dicey, and I just want to be straight up with you about where they come from. The bulk of these minerals right now come from China. Some come from Russia. Some come from Africa, from one place in Africa. I'm going to talk about that. There are some in the US. There are some in Brazil and Australia. Not nearly, you can look at the size of the circle that depicts how much of the rare earth minerals are in these locations. So Brazil, United States, Russia, Australia, they're all very, very similar. Look at how that compares to what China has, and it's not an illusion. Here it is. 87% of the world's rare earth minerals are in one location in China, and right now, China accounts for 97% of the production. So 97% of those rare earth minerals in your cell phone, in your solar panel, in your iPad, in your computer, in my computer or my cell phone, we're in this together. 97% is coming from this location in China. When you go to mine these things, they're not just sitting out there readily available. It is an energy intensive process. It is an environmentally toxic process. Look at these open pit mines and the size of the earth movers that are being used. These are all using fossil fuels to get to the rare earth elements so that they can be shipped and produced into what we call sustainable energy, sources of energy for the application cycle only. There are small mines, they're called artisanal mines, that are also beginning to produce some of these, and especially true in Africa, where very young children and very poverty-stricken adults are working in extremely dangerous, unregulated conditions to create or to bring these minerals to the surface. They're exposed to the toxins themselves. They don't have proper protection. You can see they're not wearing protection here. And often they're asked to descend into holes in the earth with very little holding those holes up. They can cave in. It is toxic for them to do this, to bring up the minerals. This is especially true for cobalt. Now, cobalt is not a rare earth mineral. It's not one of those 17, but it is a relatively rare mineral that is used in all the things we're talking about. It's needed for the magnets in the motors in the wind turbines, the magnets in the motors of the electric cars. It's needed for the lithium-ion batteries and the nickel metal hydride batteries that are being used in hybrid vehicles. So we're not often taught about this. People don't like to talk about this. Where does cobalt come from? Where does that cobalt come from? Well, it's used, as I said, in these things, the lithium-ion batteries, the motors in the cars. 51% comes from one nation in Africa. It's called the DRC, Democratic Republic of Congo. Australia fortunately produces a large amount as well, about 17%. And then it goes down from there. Other countries are producing lesser amounts. That 51% is produced in Africa, but it is purchased by China. So the cobalt is mined in Africa. It then goes to China and it is synthesized into the products that are then sold all over the world. From there, it goes to the United States, it goes into Europe, it goes to Southeast Asia and Japan. This is a sad story for me to talk about, and I want you to know where this cobalt is coming from. It's often mined in very dangerous conditions. Look, there's no struts holding the mouth of this mine. It's a hole in the earth, and these young people, they're wearing jeans and tennis shoes. To go down into these mines, the air is bad, the lighting is poor, they work long hours. A lot of times it's mined by children in labor under conditions that the United Nations, UNESCO, they know about it, they've documented it. In 2014, they said about 40,000 children were working in mines across Southern Democratic Republic of Congo. Many of them are mining this cobalt. They're doing it to help their families, but the children told Amnesty International when they were interviewed. They work up to 12 hours a day. They carry these heavy loads. They earn between $1 and $2 per day. So they're risking their lives to recover the rare earth minerals that we're being told are the answer to the problems that we're facing with climate and sustainable energy today. What does it take to manufacture these? Once they get these rare earth minerals, what happens after that? Solar panels, windmills, all these things, they are resource intensive to create. Silicon is a very interesting example. Now, I talk to young people about this and they think it's just out there. They think you just go, this silicon is out there. Silicon for solar panels has to be manufactured. It has to be produced. It is a fossil fuel intensive process. Elemental silicon cannot be found by itself anywhere in nature. It is extracted from a certain kind of quartz using heat, carbon and heat. It's called a carbothermic process that we know as smelting. The smelting cannot be driven by solar panels. It takes a very intense, high energy, and up to 5 to 6 tons. Listen to this, is just crazy. 5 to 6 tons of carbon dioxide are produced for every 1 ton of silicon that is manufactured. So for that 1 ton of silicon that's going into the clean green solar panels, 5 to 6 tons of CO2 are being produced. Some of it is released into the atmosphere. If it's a good factory, they're able to recover that. Not all of them are. Okay, and I'm giving you the documentation for all this. You can go back and look and see all the sources. So I'm not making this up, and this isn't conspiracy. This is coming from peer-reviewed manufacturing information that we simply don't talk about, typically in mainstream media. After the solar panels are made, the photovoltaic systems, they're not done yet, because now you need all the stuff to make the solar panel work. You need steel, aluminum framing. It takes fossil fuel energy to melt and create and manufacture these. Concrete, electrical inverters, copper wiring, all of this is needed in addition to the solar panels themselves. So the production obviously is energy intensive, fossil fuel energy intensive. Stage 3, what happens when a solar panel is no longer used? Well, first of all, I want to talk about performance, because there's a wide variety of performance in terms of what makes a solar panel successful. The efficiency is based upon the design and the quality of the silicon, the fossil fuel intensive process that's creating this. So that's an important factor. The efficiency of the panel is based on the layout of the cells, the size of the panel, how it's configured. And I was amazed at how many different kinds of solar panels there are. The efficiency, this is good news. When you're going to use a solar panel, efficiency has increased from 15 to 20% over the last few years, between 1995, when they were introduced, and the year 2020, when these statistics were available. But there are so many types, I won't go into all this, so many types of solar cells that are available based upon the quality of the silicon, how they're configured, how many cells per panel, and the efficiency. You can see in the upper left-hand corner, 16 to 17% efficiency for that panel. Look in the lower right, 20 to 25. Well, if I was going to do this, I'd go for the 20 to 25, but not everybody knows that. The hours of sunlight determine how effective, obviously, a solar panel can be. This is a map, a generalized map of sunlight, and you can see the orange. The oranges are where we have most sunlight. The American Desert Southwest, we all know that, through Arizona, New Mexico, parts of California, Nevada. It makes a lot of sense to have solar, but you get up into the northern latitudes, at least for portions of the year, it may not make that much sense. Here's the same kind of map, hours of sunlight in the world. So from this, we can see on the scale on the bottom, the more you get into the pinks, you've got more of the sunlight. As you go to the left, the greens and the blues, less. So Australia makes tremendous sense to have this kind of solar energy. Northern Europe, maybe not so much. Solar energy as a local resource makes a lot of sense if you are in a place that has access to it, to the light, to the sunlight, in a reliable way. So the third stage that I'm talking about here is the disposal. Where do solar panels go after they expire? This is a very sad picture telling you where they go. They go into the landfills. We're not equipped right now. They didn't think this through. They didn't think ahead. Said, solar panels are great. What do we do with them after we're finished? We're not talking about that so much. Studies have shown that the heavy metals in the solar panels, and this is coming out of Discover magazine. It was it's a lay science magazine, I think is what I would call. Studies have shown that the heavy metals in solar panels, lead and cadmium primarily, leach out of the cells into the groundwater as well as affect the vegetation. These metals are toxic. They have a record for detrimental effects on human health. Lead is commonly known to impair brain development in children. Cadmium is a carcinogen, so we don't want this stuff. But look how much we have. Now, this particular chart, part of it's outdated because the year 2017's already happened. But in the year 2017, there were 43,500 tons of photovoltaic waste in Europe. By the year 2050, what we're looking at is 60 million tons, and I believe this is Europe and North America as well. I don't want to... no, it says on the panel, it says 4 million tons installed in Europe. All right, by 2017, we had the 43.5. By 2050, the year 60 million. So this is excluding North America, this particular one. Is there a solution? So, you know, I've shared with you some of the facets of wind and solar energy that are not popular to talk about. I catch flack when I talk about it because it's easier to think that we have this panacea, that we have this utopian solution. Is there a solution? I think there are many answers that become possible. And I'm looking at near term and far term. I'm a scientist, I'm a degree geologist with a background in physics and math. And when I solve problems, I tend to look at the big picture. I tend to look at near term, now, 6 months out, and long term, 6 months and beyond. There are solutions out there. What we need, and I mentioned this in the intro, is we need a reliable base load source of energy that operates continuously under all conditions to meet the minimum power demand 24/7. It can be supplemented by solar, it can be supplemented by wind or hydro or geothermal, but in and of themselves, they cannot and will not be the answer. This is where it gets really interesting. Does such a source exist? You bet it does. And I'm going to lead into this. It's going to sound like a science fiction mystery. We're going to go back to the Manhattan Project. Northern New Mexico, Los Alamos, during the Second World War, when all the scientists came together in this super secret project to find a way to split the atom, and the end result, because it was wartime, was a wartime application. It was a nuclear bomb. In peacetime, that same technology would not have gone to a weapon. It would have gone to, to more peaceful applications. But here's what many people, when I talk to them, they don't know this. Part of what happened in the Manhattan Project was those scientists, the physicists, they went through a whole lot of elements on the periodic table to find just the right element that they needed at the time. All right? I said to you in our introduction that the scientists discovered, and I didn't tell you who, it was these scientists that discovered a source of energy. They went through all of these elements in the periodic table, and they discovered a source of energy that produces zero greenhouse gases. It's inexpensive, it can't melt down, it's abundant in the earth, its waste can be recycled into the fuel. And you say, why didn't they use it? It's because of the one I skipped. It cannot be weaponized. They were looking for a source that they could use to produce energy, the byproduct of which could be used as the weapons in the nuclear arsenal that was being developed. So they settled on uranium, whose byproduct is plutonium, and the plutonium is what's used in the nuclear arsenal. We're not in wartime right now. We don't need that. So there is an element that fits all the things I'm saying here, and the scientists have known about it since World War II. It's element number 90. It is called thorium. Thorium is a really interesting element, really interesting metal. It is abundant in the Earth's crust. I want you to look at this chart. The most abundant element in the Earth's crust is lead. You can see thorium is number 2. We're going to highlight this for you. The uranium that we're using right now, look how far down the chart the uranium is. It's not nearly as abundant. Thorium is very abundant in the Earth's crust. That's good news because it makes it accessible to all people. It's not hoarded by one nation that happens to have that supply and then uses it as leverage for other nations. Everybody's got it. It's inexpensive to produce. Now, I don't want to get too technical, but I want to make this distinction. The way that electricity is typically produced in a power plant is that water is heated to create steam, that you're seeing on the left-hand side of your screen, and the steam drives the turbines that produce the electricity that then goes out on the high-tension power lines, okay? So all these electrical plants are trying to do is they are producing the heat to boil the water and generate the steam. So in what is called a conventional boiling water reactor, BWR, what you're seeing right here on your screen, the left-hand side, what you're seeing is the uranium is being used, the uranium rods you can see, they go into a block of graphite, or different blocks of graphite, to regulate. It's a controlled chain reaction, and that chain reaction is creating heat. Heat's boiling the water, water turns into steam, and it's driving the turbine. This is a conventional reactor. What we're looking for is an element that will still heat that water, but doesn't have the drawbacks of uranium, and thorium fits the bill to the T. So the way that thorium works, the reason it's different, this is really interesting. I'm going to make a distinction here. So in a typical reactor, the water is pumped in to cool, and then it becomes heated. The uranium rods that are creating the heat. So the water, and this is the distinction. The fuel and the coolant are separate. All right. So the uranium rods and the water are separate. In a thorium fuel cycle, the fuel, the thorium, is the coolant. So the actual fuel is the coolant itself. It is called a molten salt reactor, or MSR, because the thorium is made into these thorium salts that can be used as the coolant as well as the fuel. This is such an awesome concept. So on the right-hand side, this is what you're seeing, is that the molten salt going in from the bottom is the fuel as well as the coolant, whereas the traditional reactors on the left, the water is separate from what it is that's creating the heat. So the molten salt goes in and the molten salt goes out. The way these generators, these reactors are designed is if they become too warm, because the salt is the coolant, there is a plug, it's a freeze plug that opens, and all of the material drops into separate tanks to stop the reaction. So you cannot melt down like Fukushima. You can't melt down like Chernobyl. It's impossible. It's not that it's not likely. It can't happen because the physics of how the heat is being generated are completely different than they are in a uranium-based reactor. So what I want you to see here really quickly, in a traditional nuclear reactor, it takes about 250 tons of uranium to produce, look at this, to produce 35 tons of spent fuel, 33 tons of U-238, 0.3 tons of U-35, 1 ton of fission products, and 0.3 tons of plutonium. So it is not very efficient at all. Look at thorium. 1 ton of thorium goes into the reactor, and what it does is it produces 0.0001 ton of plutonium. So it can't be used for weapons. 70% of the fusion products are stored for about 300 years. It's not optimum, but it's better than uranium and plutonium that we're talking about 10,000 years. In 10 years, 83% of the fission products are stabilized. So the bottom line, I know it's a lot of information, it's affordable. 1 ton of thorium produces the energy of 250 tons of uranium. All right. Thorium power is about $1.98 per watt versus $2.30 per watt for coal. It's even cheaper than the coal. Thorium reactors are no longer theoretical. If you Google this or you wiki this, you're going to get a lot of information saying these are theoretical. They look like good ideas, but they've never been proven. That is absolutely not true, and I'm going to show you why it's not true. They've been built and they've been used for research commercial applications in India, Germany, China, and the US. I know because I went to school close to one of these reactors and I studied and I followed when it was being implemented. In the United States, thorium reactors, Indian Point Facility, New York, 1962 to 1980. Elk River Facility, Minnesota, 1963 to 68. Fort St. Vrain, Colorado. I went to school in Fort Collins, Colorado. 1979 to 89, these were thorium reactors that were functional. They were generating electricity. They were part of the power grid, and then they were shut down. So let's go back to where we began. Carbon dioxide. We're trying to eliminate the carbon dioxide going into the atmosphere. The emissions from carbon dioxide, 36% come from natural gas, 45% from oil, 19% from coal. All right? So when we look at this 80% of fossil fuels, if we could replace that 80%, look at this. If we could replace that 80% plus, we're going to back up here. If we could replace the 80% that right now is based in fossil fuels plus the 8% that is a nuclear reactor that people are afraid of and have problems, if we could replace all of that with 89% thorium, 11% renewable, this is what the equation would look like. 89% thorium. It is a reliable source of base load energy. If we want electric cars, we're going to need a lot of electricity. If we want electric factories, if we want electric industry, if we want to build these things out the way we're talking about building them out, we need this reliable source of energy, and the materials that are based in the rare earth mineral industry are simply not sustainable. They're not reliable. Now, is thorium the answer forever? Absolutely not. It is a short-term answer. We could start doing this in this year because these facilities have already been tested. Thorium is a bridge to sustainable energy. So what is the ultimate sustainable form of energy? This is where it gets really, really interesting. We know that we are surrounded by energy and we're learning through new physics to tap into that energy. The quantum vacuum. Empty space, it's not really empty. In 1 cubic centimeter of space, about the size of a single white sugar cube, the energy density is 10 to the 93 grams per cubic centimeter. What does that mean? 10 with 93 zeros after it. Grams per cubic centimeter, that is how much energy is available to us in 1 sugar cube space of the vacuum around us. And there are physicists, I'm friends, and I'm with many of the researchers that are studying and developing technologies, and I think we'll probably see this in our lifetime. This isn't like, our children's children. But right now, ultimately, all of this thorium, uranium, solar, I think all of those will be replaced by what is called the quantum vacuum density energy or fluctuations in the quantum vacuum. Ultimately, that's where we're going to go. And I wanted to say that to round this out. But we're being told we're in crisis right now. We're being told we've got to do something right now. But what we're being asked to do doesn't make sense when we look at the cycle of production and disposal as well as the implementation, where the materials are coming from, who is providing those materials, who's going into the earth and mining it for us. The solutions we're being given, in my opinion, this is my opinion, are not the best solutions we have available to us. So I wanted to share this with you. I wanted to say this. Ultimately, the source of energy is going to be the vacuum, and that's where we're going to be. Star Trek is going to be in our living room, and that science fiction will become science fact, as I mentioned, in our lifetime, because the technology is moving so fast. It's already there. It just is not perfected commercially yet. But in laboratory settings, scientists are already able to tap this form of energy. So I hope this has been useful to you, and I hope it hasn't. I hope it has been uplifting in the sense that we already have a solution if we have the political will, if we have the knowledge, if we have the demand to bring into our lives what we developed 60 years ago. It is a message of hope and possibility. And also, I want to be very, very clear again. I love solar. I love renewables. I love wind where it makes sense to have them. Realistically, as I mentioned, they cannot be the ultimate solution. I think they are regional solutions that feed in to this baseload power. I've given you the reasons why I think this. I hope this has made sense to you. I hope you've enjoyed sharing this as much as I've enjoyed sharing it with you. Let me know when you see this video. Let me know how you feel about it. Write in the comment section. You can write to the office, Wisdom Traditions, with comments. And I'd be really interested to know how this has sounded to you, if I have found the words to convey in a truthful, honest, factual way what it is that we're up against and what options we have available to us. So until next time, thank you so much for sharing this episode of Science, Policy, and Politics. I look forward to our next.